This is AP Calculus Function Analysis Analytically, and this is going to be a homework help video, and it says here use the instructions for problems 1 through 5. During class we worked out problem 1, and as homework I assigned problems 2 through 5. I have agreed to work out on video for homework help purposes problems 3 and 5 in this set. So let's go over here to take a look at, so I'm going to work out 3 and then also 5. So anyway, we have these 5 things. A, all critical numbers. Well, the critical numbers are found where the first derivative is equal to 0 or undefined. And so for this, I'm going to consider this as a product of two functions. So to make a product of two functions, I like to define the two factors as u and v. And so the upper right, I'm going to construct a little box here, which I use sort of as a graphic organizer to keep myself straight. So what I'm going to do is I'm going to say the upper left cell is u, the upper right cell is u prime, the lower left cell is v, and the lower right cell is v prime. And so u is x, and then u prime is the first derivative of x, which is 1. Then for the other factor, we have this quantity x minus 4 cubed, and then for v prime, we have 3 times quantity x minus 4 squared times the derivative of the inside, which is 1. So that's what we have here. So we say f prime of x is equal to uv prime, which is going to be x times 3 quantity x minus 4 squared plus vu prime, which is going to be 1 times quantity x minus 4 cubed. And so that's going to be it. Now we're going to continue f prime of x and just sort of simplify things. We look for common factors on either side of this plus sign, and we see that we have x minus 4, quantity x minus 4 squared is a common factor between these two entities. And then we have times what? We have x times 3, so that's going to be 3x. And then we have plus this x minus 4. Okay, so that's what it looks like. And then just simplifying out, we say f prime of x equals quantity x minus 4 squared. And then this 3x plus x minus 4 is going to be 4x minus 4. So now using the zero factor property, our critical numbers are going to be found where either x minus 4 is equal to 0, or where 4x minus 4 is equal to 0. And solving for x, we have x equals 4. And for this other equation, if we add 4 and divide by 4, we're going to have x is equal to 1. So now, and again, so these will be our critical numbers. Okay, I'll put critical and this is going to be part A. Okay, next, determine intervals where a function is increasing or decreasing. Justify. I'm going to come over here to the up here and make what I tell my calculus students are friends, which would be a number line. So I'm going to evaluate this number line, and the critical numbers 1 and 4. Now I'm going to put f prime above the line and f below. And we'll just check for plus or minus signs. Now, what we have is this function right here, f prime of x equals quantity x minus 4 squared, and then 4x minus 4. We'll try numbers in different places in these intervals. Well, a number less than 1, we can plug in 0. Well, first thing we should notice is that this quantity x minus 4 squared is always going to be positive. Why is that? Because that can never be negative. When you square a negative number, it's going to be positive anyway. So this entity is always going to be positive, except where it equals 0. So that's always positive, and then if we plug in 0 for here, we get a negative. So a negative times a positive is negative, so we are decreasing here between negative infinity to 1. And then to the right of 1, we can pick 2. Well, this is always going to be positive, but then if we pick 2, this is going to be positive also. So we will be a positive times a positive, increasing. And the last interval is also going to be positive times positive, because this thing here will still be positive, and this one on the left is always going to be positive. So this is what the number line diagram looks like. And so we will say f of x is increasing on the intervals. Well, we're starting to increase it at 1, so we'll say 1, and you could actually use a bracket instead of a parentheses, 1 to 4, and also 4 to less than infinity. Now you can actually lump these together in one single interval, because even though we're going to 0 at 4, the thing is still increasing all the interval from 1 toward 2 less than negative infinity. But we'll just leave it like this. F of x, justify. Why? Because f prime of x is greater than 0. Okay? And then also, where's f of x decreasing? It's on negative infinity up to 1. Why is that? Because f prime of x is less than 0. Okay. Well, so that'll be part B. Part C, determine where a function has local maximum, minimum, then value of extreme. For part C, we have a local minimum, so local or relative minimum at x equals 1. And why is that? Because f prime of x changes from negative to positive. Okay, and this says find the value of that extreme. So we will plug into the original equation. We will say f of 1 is equal to 1 times 1 minus 3 cubed, which equals 1 times negative 3 cubed, which equals negative 27. So we'll say relative minimum of negative 27, where x is equal to 1. It says relative minimum, and I think if we diagram this, I believe we're going to be an absolute minimum as well. But it is, let's say, searching relative is also a relative minimum. Okay, D, determine intervals where a function is concave up, concave down. And so for part D, I'm going to bring this function right here that we have. We have f prime of x is equal to quantity x minus 4 squared times 24x minus 4. And we're going to do the similar situation that we did on part A. If we set these up as UV, and I'm going to come over here to the right again. Okay, we set up this box, UV. So I'm going to say U prime, V prime, and we say U is quantity x minus 4 squared, so we say x minus 4 squared. And for U prime, we take this 2, so we have 2 times quantity x minus 4. And then for V, we have 4x minus 4, and V prime, we have 4. So f double prime, second derivative, is equal to U V prime, so we'll say 4 times quantity x minus 4 squared plus V U prime. So we have this 4x minus 4 times what I'm going to do is I'm going to put this 2 out front, right? Because I had 2x minus 4. So 2 times quantity 4x minus 4 times quantity x minus 4. And then we look for a common factor in the midst of this, and looks like we have one of x minus 4. So f double prime, we bring up this x minus 4. And what do we have left? Well, we're going to have 4 times x minus 4, right, because we still distribute that, plus 2, and we factored out this x minus 4 already, so we'll have 2 times quantity 4x minus 4. Okay, and then f double prime, just simplifying, is going to be this quantity x minus 4 times, okay, we're going to get 4x minus 16, right? 4x minus 16, and then we're going to have plus 8x, and then we're going to have minus 8. So we're going to get f double prime of x is equal to quantity x minus 4 times, just simplifying here, we have 12x, and then negative 16 minus 8 is going to be minus 24. So the potential points of inflection are going to be where, using the zero factor property, we set 0 equal to x minus 4. So x equals 4 is a potential point of inflection. And then also we set 0 equal to 12x. And I'm going to factor this out. 12 times quantity x minus 2. So we can also have x equals 2. So these are called our possible points of inflection, which I abbreviate PPOI. Okay, now I'm going to create another number line up here. This time testing for concavity. And I set these values here at 2 and 4. And above here, I'm going to put f prime. And down here, I'm going to put f, just f. So we evaluate, like less than 2 would be 0. We'd have a negative times a negative, so we'd have positive. So we'd be concave up in this interval from -infinity to 2. And then between 2 and 4, something like 3, we would have a negative, and this one here would be positive. We'd have 36 minus 24, so we'd have a negative times a positive, which would be concave down. And then to the right of 4, we would have greater than 0, greater than 0, so we'd have this kind of arrangement here in the number line. So we're going to say concave up on interval -infinity to 2, and also union 4 to infinity. Why? Because f double prime of x is greater than 0. And then concave down on 2 to 4, interval of 2 to 4, because f double prime of x is less than 0. Okay? And then finally it says E, determine where function has points of inflection. E. Okay, point of inflection at x equals 2 and x equals 4, because f prime of x, f double prime of x, changes from positive to a negative, or from negative to positive. So there we have parts A, B, C, D, E. Next, I'm going to look at working out problem 5. You have f of x equals this x squared minus 4 over x plus 2. And this function really does simplify out because I believe we can factor. So we can, this numerator is going to be quantity x minus 2 times quantity x plus 2 over x plus 2. So we have quantity x minus 2, but we know our function is undefined where x equals -2. All right, so that's going to be probably some kind of critical number at some level. So let's just go ahead and continue working through this. Again, we have a quotient of two functions, so we have a high and a low. So our high is equal to x squared minus 4. Our d high is equal to 2x. Our low is equal to x plus 2. Our d low is equal to 1. So f prime of x is equal to low d high. Well, low is going to be x plus 2. D low, low d high, so d high is 2x, right? Minus high, and high is going to be x squared minus 4, d low, which is 1, all over low squared, so that's going to be quantity x plus 2 squared. And then just working to the right, we're going to have x times x, we get x squared. No, it's going to be 2x times x, so that would be 2x squared. And then 2x times 2 will be plus 4x. And then we're going to have minus x squared. And then we're going to have minus negative 4, so plus 4, all over low squared, which is going to be x plus 2 squared. So we're going to get 2x squared minus x squared. We're going to get x squared plus 4x plus 4. And that's going to be over quantity x plus 2 squared. So we have here a situation where if we set this equal, our numerator equal to 0, we say 0 equals x squared plus 4x plus 4, and that's going to be equal to quantity x plus 2 squared. And then that's set, and so our critical number is going to be x. If we set x plus 2 equals 0, we have critical number of x equals negative 2. And then our denominator, likewise, we can set it 0. So we say, okay, it's the same thing, right? X plus 2, x plus 2 squared equals 0. So we say that's also critical number of negative 2. So this would be a single critical number. Okay, critical number of x equals negative 2. And it says determine intervals where function is increasing, decreasing, justify. Well, we know we have a critical number of negative 2. Okay, that's part A. Part A. B, we say, okay, we have a number of negative 2. And we're going to put f prime here above and f below. I think I know where this is going to go. And so we have this function right here. We have essentially, you work this all out to the right, you just have x squared. Well, really, it's going to simplify to quantity x plus 2 squared over quantity x plus 2 squared. So you can take a number less than negative 2. These things are always going to be positive, right? Or potentially 0. And so we're going to be positive, so we're going to be increasing. And then greater than negative 2, we're still going to be positive, so we'll be increasing all throughout, except where x equals negative 2. So we will say increasing on a negative infinity to negative 2 union negative 2 to infinity, and that's going to be because f prime of x is greater than 0. And we have just, do we have a local max or minimum? So we say no. That's part B. Part C, no local extrema because f prime of x does not change from positive to negative or from negative to positive. Okay, determine intervals where concave up, concave down justify. Well, really, we're talking about a line because this whole thing is going to simplify to 1, and at least the slope is going to simplify to 1, right? And then this is going to be x, well, except at 2. So the slope is going to be 0. So if we set that equal to 1, f double prime of x equals 0. So but that's going to be everywhere. So there are no points of inflection. So that's going to be part, and no concave up, concave down. So that's going to be it. Good luck, and as always, thanks for viewing.